How do video game graphics work? Have you ever wondered how video games take you to distant planets, magical lands, and mystical adventures, all from the comfort of your home? What makes these worlds come alive? In this episode, we're diving deep into the fascinating world of video game graphics. We'll explore how these digital realms are created, the technology behind stunning visuals, and the incredible process that transforms lines of code into breathtaking landscapes and characters. So sit back, relax, and prepare to be amazed as we unravel the secrets of video game graphics. Okay, so let's start with the big question. How do video game graphics work? Well, it's actually a pretty complex process involving a lot of math, clever algorithms, and some seriously powerful hardware acceleration. But don't worry, we're here to break it down for you in a way that even your grandma could understand. Just kidding. Maybe not your grandma. But basically, it all starts with the code. Video games are ultimately just lines of code that tell the computer what to draw on the screen. But thanks to some really clever programming, these lines of code can create some truly amazing things, like the character you control or the environment they inhabit. These elements are called assets. And there are three main types of assets that make up the graphics of a video game: 3D models, textures, and shaders. 3D models are exactly what they sound like: three-dimensional objects that can be manipulated in a game engine. Everything you see in a video game, from the hero to the henchman to the huts in a far-off village, is represented by a 3D model. These models are made up of polygons, which are simply triangles. Yep, everything you see is made up of triangles. It's kind of crazy when you think about it. The reason why 3D models are made up of triangles is because they're really easy to calculate mathematically. A triangle has three vertices, which are the corners of the triangle, and three normal vectors, which define the direction the triangle is facing. With this information, the computer can calculate how light will reflect off the triangle and how it will appear to the player. Shaders are basically programs that run on the graphics card and define how light should interact with a surface. For example, shader might define how light is reflected off of a shiny surface like a mirror, or how shadows are cast on a rough surface like concrete. Now that we've covered the basics of 3D models, textures, and shaders, let us take a look at how they come together to create the stunning graphics that we see in modern video games. The process begins with the game engine, which is basically the software that runs the game. The engine takes all of the assets like 3D models, textures, and shaders, and combines them to create a single image that is displayed on the screen. But this doesn't happen all at once. Instead, the engine breaks down the scene into a series of smaller steps that are executed in parallel to make sure that everything runs smoothly. This is called the graphics pipeline. The first step in the graphics pipeline is vertex processing. During this stage, the engine takes the 3D models in the scene and positions them in the game world using something called transform matrices. These matrices are basically arrays of numbers that define the position, rotation, and scale of an object. The engine then uses these matrices to calculate how each object will appear to the player from the camera's perspective. This includes calculating the object's position, size, and orientation in the 3D space. Next up is rasterization. During this stage, the engine converts the 3D shapes in the scene into 2D pixels that can be displayed on your screen. But wait a second. How does a computer turn a 3D world into a 2D image? Well, it does this by projecting the 3D scene onto a 2D surface, sort of like how a camera projects the world onto film. But unlike a camera, the computer has to do this in real time, which means it has to execute this projection algorithm millions of times per second. Once the 3D shapes have been converted into 2D pixels, the engine needs to figure out which triangles are visible to the player and which ones are hidden behind other objects. This is done through a process called depth testing. The engine compares the depth of each triangle to the depth of the triangles in front of it. If the engine can see one side of a triangle but not the other, it knows that the triangle is visible and will draw it. Otherwise, it will skip over that triangle. Next up is pixel shading, also known as fragment processing. During this stage, the engine applies lighting, shadows, and textures to each individual pixel in the image. This is where shaders come into play. The engine uses small programs called shaders to apply lighting, shadows, and other effects to each pixel. For example, a shader might take into account the position of the sun, the color of the sky, and the material properties of an object to calculate how light should reflect off of its surface. One particularly cool use of shaders is in video games that feature reflections, like a mirror or a puddle. In these cases, the shader can take the color information from the surrounding environment and reflect it onto the surface, creating a realistic-looking reflection. This is accomplished by sampling the color information from the pixels around the current pixel and using that information to calculate the color of the reflected light. Of course, this process is happening millions of times per second for every frame of the video game, which means that shaders need to be very efficient and fast to execute. The next step is post-processing, which is where the final touches are added to the image. This includes things like motion blur, anti-aliasing, bloom, and color grading. Motion blur, as you might have guessed, adds a sense of motion to the image by blurring pixels that are moving quickly. Anti-aliasing, on the other hand, is used to smooth out jagged edges in the image. Bloom is an effect that simulates the distortion caused by bright lights, and color grading is used to enhance the overall look of the image. These post-processing steps are often executed on a separate render pass, which means that they are applied to the image after the initial rendering process is complete. This allows for more flexibility and enables developers to add new post-processing effects without modifying the core rendering pipeline. So there you have it. That's how video games go from lines of code to beautiful, immersive worlds. Now that we've covered the basic pipeline, let's take a look at some of the key technologies that make realistic graphics possible. Ray tracing is a rendering technique that simulates the behavior of light waves as they interact with objects in a scene. Unlike traditional rendering techniques, which rely on approximations and estimations to calculate how light behaves, ray tracing actually traces the path of individual rays of light as they bounce and reflect in a scene. This allows for highly realistic lighting and reflection effects, but it's also extremely demanding from a computational standpoint. Ray tracing was first introduced in the 1970s, and it was until relatively recently that hardware-accelerated ray tracing became available in consumer graphics cards like those from NVIDIA SRTX line. This has allowed for some incredible lighting and reflection effects in modern video games. Global illumination, also known as GI, is another important technology that contributes to realistic graphics in video games. GI calculates how indirect lighting works in a scene, essentially how light bounces off of one surface to another and illuminates an object from an indirect source. This is important because in the real world, indirect lighting is responsible for a significant portion of the illumination in many scenes. For example, if you're in a room with a window, the light coming through the window is direct lighting, but the light that bounces off the walls and ceiling is indirect lighting. Without GI, video game graphics would lack the sense of depth and realism that we've come to expect. Unreal Engine 5's new rendering system, Lumen, uses a technique called path guiding to accelerate the calculation of global illumination in real time. This allows for dynamic changes in lighting and reflections as the player moves through the game world. One of the biggest challenges in video game development is balancing visual quality with performance. This is especially true when it comes to features like ray tracing and global illumination, which can be extremely demanding on a computer's graphics card. However, recent advances in machine learning have led to the development of AI-based supersampling techniques like NVIDIA DLSS and AMD SFSR. These techniques use machine learning to train an AI model that can upscale a lower resolution image to a higher resolution image without losing any visual quality. This means that games can be rendered at a lower resolution, which is less demanding on the GPU, and then upscaled to a higher resolution using AI, resulting in better performance without sacrificing visual quality. Another important aspect of video game graphics is the ability to simulate physical phenomena such as cloth, hair, water, and destruction. This is done using physics simulations, which are calculations that simulate the behavior of real-world objects under the influence of forces like gravity, wind, and collisions. Physics simulations are typically handled by a physics engine, which is a piece of software that performs these calculations in real time. One widely used physics engine is NVIDIA PhysX, which is used in many popular video games to simulate things like cloth, hair, and destruction. as you've seen. Creating realistic graphics for video games is a complex and multifaceted process that involves a combination of clever programming, advanced rendering techniques, and sophisticated physics simulations. From the way light interacts with objects in a scene to the movement of cloth and hair, every aspect of a video game's graphics is carefully designed and calculated to create a truly immersive experience for the player. And as technology continues to advance, we can expect to see even more realistic and breathtaking graphics in the future. But what does the future hold for video game graphics? Well, there are a number of exciting developments on the horizon that promise to push the boundaries of what is possible. One of the most notable of these is Nanite, which is a new micro-polygon geometry system developed by Epic Games for their Unreal Engine 5 game engine. Nanite allows for the rendering of millions of polygons in a scene without any slowdown or decrease in visual quality, which opens up new possibilities for creating highly detailed environments and characters. Another exciting development is path tracing, which is a rendering technique that traces the path of light rays to create incredibly realistic lighting and reflection effects. Path tracing has been used in computer graphics research for decades, but it has only recently become possible in real time on consumer hardware. This means that we may soon see video games with lighting and reflections that are indistinguishable from real life. Finally, AI-generated assets are also starting to make their way into video games, which means that textures and models could be created by neural networks trained on millions of images. This could potentially revolutionize the way video games are created by allowing developers to generate new assets at the click of a button. Overall, the future of video game graphics is looking brighter than ever. With advances in technology, we can expect to see more realistic, immersive, and breathtaking graphics in the years to come. And there you have it, folks. That's how video game graphics work. From the way light interacts with objects in a scene to the movement of cloth and hair, every aspect of a video game's graphics is carefully designed and calculated to create a truly immersive experience for the player. And as technology continues to advance, we can expect to see even more realistic and breathtaking graphics in the future. Thanks for watching, and I hope you learned something new. If you're interested in learning more about video game graphics, I highly recommend checking out the courses on a popular learning platform. Until next time, happy gaming.